Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do a very simple session. So this is a 2D heat transfer problem. So we'll do conduction and convection mode, and in this particular 2D heat transfer model we'll start with a steady state condition. So what inputs required for a steady state condition, how you can model a steady state condition versus what is the input required for a transient model. So this is exactly what we are going to do. So right now on my screen what you see is a temperature profile for a steady state condition. So we one end we are given 100 degree C, we given some film coefficient along vertical lines and horizontal lines, and this end we put a insulation, so you see quite a bit temperature gradient. So this is the problem. We are going to do it, and I think it's very straightforward. The learning in terms of this is like you learn how to model a steady state condition, transient condition. You can know how you can give a different film condition. So that's what actually we'll do. So let's quickly go through the problem definition and some basics, and then we'll start modeling the problem. So as I mentioned, we are going to talk about steady state condition. So what inputs you required for steady state condition versus transient heat transfer. So quickly touch base with heat transfer basics. So you have three different types of heat transfer. One is conduction. So if you take a rod and one end is you start heating, the heat transfer through this is a conduction, and the parameter which you required for this is a conductivity K. Now if you stand somewhere here and there is a bonfire and you try to take a heat, this is a convection heat transfer. So this is nothing but your HA dt by delta T. So this is your Q. Here Q is Ka dt by dx. And if you get a heat from sun, this is nothing but emissivity into temperature raised to 4. So this is a radiation problem. So this is exactly what they are saying. It's if anything transfer through solid. So heat transfers through copper or steel or wood or soil, those are purely by conduction. If moving air come or you are sitting, there is a fan going on and you sit under the fan, then this is a convection heat transfer coefficient. So H A delta T, that is going to conduct this. And then convection heat transfer coefficient is depend on view factor. Suppose I put a umbrella here, so my view factor is different, so you will not get this conductive heat transfer is again radiation heat transfer is multiplied by the K view factor. So you have different view factor. So you have different option, surface 1, surface 2, how is the view factor and the emissivity part. The problem which we are going to do is a 2D steady state problem. We are going to concentrate on difference between steady state and the transient heat transfer. We'll do some calculations. So this particular problem is a combination of these two. Radiation we are not going to take it in this problem, but later on we can add the complexity in terms of radiation. So specific problem what we have taken is this is a 2D. So this is a 2D problem. We have taken the length 1 meter, width is 0.6 meter, and somewhere around this is around 0.2 meters will measure what is the temperature there. One end will give temperature condition, so 100 degree C, and then will give the H on this and this. This is fully insulated edge will be there. There is no heat flux going through this, and this H is there will be H of the temperature of surface and temperature of ambient. So based on this you can get a convective heat transfer going out. So we'll give temperature, the heat move through this is conduction. So steady state conduction Fourier law is K A dt by dx. So the area, you'll finite element modeling will calculate the area based on the geometric configuration. This will be the perpendicular area to the heat flux. K is the conductivity of material, so we already taken the conductivity of material 52. These are SI units. And then if this start getting heating up, the heat from here to environment go using convection heat transfer, which is nothing but H A delta T. This delta T is nothing but T surface minus T ambient, and this H is again depend on the different condition. You put a fan or you give natural convection where actually the air comes closer to the heated surface, and then density reduce, so it's move up, and then natural convection, or it's depend on different conditions. So the film coefficient, what we are going to use, a 750 on the both edge, and then heat will go out from this using convection, and then we'll measure what is the temperature at this 0.2 meter. Now since we are using this steady state condition, so we just required a input like conductivity, which will give area, we know, one in temperature boundary condition we are giving, Lx we know from this length, film coefficient we are going. So this is exactly the problem. We'll try it, and then later on we'll convert this problem into conduction transient problem. So let me clear this. So we'll create 2D planar problem, and then shell size approximately 4, so I'll just put 0, 0. So I got this. Then I'll put 0.6, 0. So I got this x parameter 0.6, 1. So I get a height and 0, 1. So I can easily build a plate. So I built a plate. Done. I'll require one more point here, somewhere 0.2. So I'll just cut it this using datum plane. So I take a datum plane perpendicular to y, which is nothing but xz, and then I'll put 0.2, and then I'll just trim it. So face I'm going to trim with datum plane, and then I'll say partition done. This is a standard problem in Abaqus tutorials. So you can also refer a 2D heat transfer problem, and this is mainly Abaqus benchmarking problem. So they done a benchmarking with this problem. Property will put, so it's a steady state condition, so we required conductivity, which is ours conductivity is 52. That's what actually we want to do, and then we'll create generalize 2D. No, sorry, this is not I not choose the correct one. So I'll show you. You have to select solid, homogenize, and then we'll say it is a 2D problem. So you selected that. We'll quickly assign this. So we assign this. So we created a property, everything. We'll go to the assembly. We'll create the assembly. We're done the assembly. We'll create the step. So it will be steady state heat transfer, and then we'll give, so It is steady state, so time period doesn't matter, so we put 1. We can have increment 1, mini initial 1 and maximum 1, but we'll have just 0.1. So we can see how over a period of time this temperature is increasing. Not over a period of time, but just to see every step how this is getting applied. Nothing more than that. We'll just do that. Then interaction, we have to define the film. So we want to define a film coefficient on this vertical and the top edge. So this is one of the important learning for you. So this interaction, you go to interaction, you go to the interaction property, and then you can see surface Philip condition, and then there are two things required is the H parameter. So film coefficient we mentioned 750, and the sink temperature. So sink temperature we are taking as a 0. Then we'll have one more at the top. So you select the top. Let me create it. And this is 750 and this is 0. So we define whatever the require for conduction heat transfer. We also define a convection heat transfer. Now will give boundary condition is temperature boundary condition. So this particular age is at 100. That's what we are given. Now we'll mesh it. So again, my favorite one, middle axis. That's what actually I like. This we can say 0.05, or we'll put 0.005. Now this is too much. 0.01 we'll put. 0.01 is good enough. Then we'll say select the heat transfer. So this is nothing but DC to D4, so a 4 noded linear heat transfer quadrilateral, and we'll just put a mesh, and I'll just create couple of set. Measure, so I'm just going to measure here. So I put there 1, and then I'll create all node set, because we need to give what is the initial condition. So initial condition, the plate is at 0 degree C. So that will applied in loads. So you go to the loads, you see the counter plot. This is a predefined phase, and then you say initial others. My temperature on this all plate is 0 degree C. So that's all actually we are done. So it's almost ready to run. But just quickly recap, this was steady state condition. So the material property what you need to give was conductivity, which you are given. Then we are given H you have to give in interaction. You click it, you can give film coefficient and sink temperature. This is also important, what sink temperature is there. This can be a temperature dependent if you want to do a non-linear heat transfer analysis. Then you have to really create temperature versus film coefficient data. So that also you can do user defined or property reference. So let me save this. So steady state heat transfer, and we'll run it. So let's do a data check. We are not asked for any history output. So this is a data check. So data check is complete, no issue. So we just submit the run. So run is completed. We'll check results. So we'll look for, and then this is a steady state condition. You can also query prop value and then select the nodes. So it is something like a 23. You can also, the different way you can also select. So this is what you see, 23, what's exactly what we are seeing. So node 158, it was 23.28. Now now specifically we get this gradient because this is insulated surface and the heat is going out from this side. Now quickly we'll look for doing a transient model. Now transient, then there are inputs will change. So there is a, when we talk about transient, the inputs will be then coming is time. So there is a time will come. Now once for the transient, there is other one more governing equation will come in picture other than the conduction and convection. Q is mCp delta T. Cp is nothing but your heat capacity. So how much heat is required to raise a 1 kg mass by 1 degree? That is nothing but what is your governing equation come. So you required a mass input, you required a Cp. Cp, specific heat of steel, we already know it's a 134. Then you have to have a density also. So density into the volume, it will calculate what is a mass Cp, and then from initial temperature, initial condition, if it has to raise by 1 degree, how much is heat required. So this is additional, the heat capacity equation will come along with your Ka dt by dx. This is for conduction, and Q is equal to HA T surface versus T ambient. So H already you are giving, K already you are giving. So this was only for steady state. Now once you want to do a transient one, this is the additional one. So the plus one is mCp delta T. Then you have to give specific heat, you have to give mass, and then there also one more input will come, time. At what particular time you want to do this. So it's like 1500 seconds we are going to do. So same problem will do, but a 2D transient problem. So what I'll do first, I'll delete this step. I'll go to the property, I'll edit it, and then I'll first add density 7850, and then I'll add a specific heat. So 434 is my specific heat. So I added the required things on that. Then I'll just create a step. This will be transient and then hit transfer. Then you have to give actual time. So we are going to run it till 1500 seconds, 15,000 seconds. Then the other thing is initial condition you have to give. So I'm going to give 1. Then maximum allowable temperature per increment, I am saying it's a 10. And then this is also, if you want, you can use end time when temperature change is less. You can use this also if you want. So if something like temperature rise is very low, so something like 0.005, we can say steady state condition is achieved, so there is negligible change in temperature, you can stop this analysis. This is not required. In case you want to add, you can add it. Otherwise just add maximum allowable temperature change per increment, then you start with initial and then 1500 and see how the analysis looks like. So we done that. Now we'll quickly go to interaction because we already deleted the last step. So this will surface 1 will put 750 sink temperature 0. Why we are doing it again? Because the earlier definition was inside the step. That step we are deleted, so new step we have to give it again. So we done this. Look for a load, create. So we are going to give temperature here, we are going to apply immediately. So we given a boundary condition, initial condition already is there. This was not inside the step, so you don't have to worry about that. So we are done it. So let's save the file. Transient, hit transfer, and then we'll quickly run it. So job will create transient, hit transfer. We'll have quick data check. We are not asked for any history output, so we'll have quick data check, and then we'll see how the transient model looks like. So it's given. It's completed. So let's submit it and then wait. So we have submitted now for the transient heat transfer thing. Quickly monitor it. Input pre-process done, standard started. So you can see, we'll see the increment, how the increment is going on. So it started with time is equal to 0, then it's just keeping up. So we already done it. So let's check the result. So we'll look for a field output temperature, and then we'll measure how the temperature is moving over a period of time. So this is how. So this is actually a transient problem. So you given heat, then how slowly heat is propagating. So you see, this is the way heat is slowly propagating outside. You can also plot XY data. And then node, you can select 158 or any node you can split, and then pick from. So you pick any node and then plot it. So this is what exactly you look. So it started with 0, slowly temperature is, and then you get a steady state condition. So your time versus temperature for specific node, and then you can see how the data is moving from one end to another. The major thing is then you can look into how the heat is getting transferred from one end to another end over a period of time, and then you can plot the specific node anywhere you want to measure the time versus temperature data. So this was our basic video in terms of heat transfer modeling within Abaqus, which is straightforward. So overall summary out of this analysis is, one thing is like for steady state, the governing equation, steady state for conduction and convection. So the governing equation is Ka dt by dx. This is one, and for convection it will be H A T surface versus T ambient or sink temperature. In case of transient heat transfer model, along with these two, this and this, and then you have to have one more is MCP delta T. So for transient model you have to give specific heat, for mass you have to give density, you have to give K, you have to give H, and along with this you have to give a time. So this is a quick video on the steady state and transient heat transfer modeling. Hope you like this video, and which will be useful for you. Thanks a lot for listening to me. Thank you. Bye bye.